Hello there, I'm Thomas Hatsios, the pilot captain flying the Boeing 777-300 ARX in tonight's flight from Zurich International Airport. We're going to be overflying Zurich, Switzerland, Germany, and then coming back at Switzerland and Zurich International Airport, runway 14 for landing, ILS localizer landing. As I said, we're flying the Boeing 777-300 ARX, so 50 PMTG simulations and Microsoft Flight Simulator X. So thank you for joining me. I'm gonna start showing you right now I'm in the cockpit for the takeoff preparation. So I'm gonna start showing you the cockpit instruments and the displays of the Boeing 777-300 ER aircraft. So this airplane it has a primary flight display with a flight mode annunciator and flight director and autopilot command. You can see in the primary flight display we have the airspeed display, the barometric altitude above the sea level, the rate of climb and descent in feet per minute, tens, hundreds and thousands of feet per minute, the radio altitude above the ground level, the magnetic heading or true heading using the magnetic compass and tracking the magnetic or true north pole. Because we have a difference between the magnetic and true north pole depending on where we are in the globe, the magnetic variation. We have the horizontal situation indicator and the altitude indicator with the flight director crossbars and the pitch ladder in degrees and the bank angle limits. We also have the autopilot flight director command crossbars and the ILS localizer crossbars with the horizontal and the vertical glide slope. So We also have the airspeed selected and the altitude selected from the autopilot and flight director system panel. I'm gonna show you also the autopilot flight director system panel of the Boeing 777-300ERX airplanes. So we also have the flight mode annunciator in the primary flight display. That displays the auto throttle, auto thrust, and autopilot vertical and horizontal navigation modes. So we also have the navigation display that displays all the airports, the waypoints, the VOR, ADFs, NDBs, the radio navigation, and the magnetic or true compass, the track of the aircraft, other aircraft that fly around us, and also the weather and terrain radar display. We have the terrain reflections right now, the terrain map displayed in the navigation display with the terrain levels in thousands of feet. So we also have the GPS position of the aircraft and the flight plan we create using the flight management computer. We input the data of the aircraft in the flight management computer, and we create a flight plan of the aircraft. We can fly using the autopilot, or we can fly using our manual flight control input. So flight control and thrust levers input. So I'm gonna show you also the autopilot and flight director system panel. We have also the autopilot engage and disengage switches. We have the auto throttle left and auto right engage and disengage switches. We have the airspeed select knob and the airspeed modes. So maybe I'm gonna start showing you in a couple of minutes. So we have the glide continues. We have the auto throttle hold switch. We have the flight level speed change. We have the vertical and the horizontal navigation modes of the flight management computer, which are connected to the autopilot flight director system. We have the bank angle limit and the heading select knob, and also the heading select the heading hold switch. We have also the vertical rate of climb and descent for the autopilot command with the flight director. So we can select the rate the aircraft is climbing or descending in tens, hundreds, or thousands of feet per minute, or in a trigonometric angle in degrees. So we also have the vertical speed or flight path angle, the FPA, the OVS hold switch. We have also the barometric altitude level select knob, and the barometric altitude hold switch for the cruise level of the aircraft. So I'm gonna show you also the ACAS, the upper and the lower ACAS, the engine indication and crew alert system displays that display permanent and engine data from the FADEX, the full authority digital electronic control computers, one installed per engine, controls the engines and monitors and displays all the parameters. I'm gonna show you like the N1, which is the low speed, low pressure compression stage of the engine, the exhaust gas temperature, the outflow valves from the engines, compressor, the duct pressure. We also have the N2, which is the high pressure, high speed rotor stuff state of the turbofan engines, the fuel flow per engine per hour in thousands of kilograms or thousands of pounds, and the oil quantity, the oil temperature, and the vibration of the N2 stage of the engine. These are the permanent data in the upper ACAS, and we can select in the lower ACAS engine indication controller system display other systems also besides the engines. I'm going to show you also that. So we also have the thrust levers. We use the thrust levers to modify the thrust created from the engine. We have also the flight controls, wheel, the vertical column and the control wheel of the aircraft. That controls the elevators, the vertical stabilizer using the rudder pedals, and also the ailerons and the spoilers using the control wheels. So I'm going to show you how to use the flight controls and the secondary flight controls, the flap and the slats and the speed brake. We have quite many things to show you. We also have the stabilizer train, position, normal and alternate, and the speeds in the control wheels. So I'm gonna show you as many things as I can, as far as I can. So I'm also gonna show you the navigation and communication panel, the overhead panel. We have in the overhead panel the electrical system, the left and the right engine driving alternators. We have the APU, the auxiliary power unit. We have the ADIRU, the air data and SR reference unit, the flight control computers, the left and the right engine hydraulic pumps, drives, and uh, the backup electrical for the hydraulic. Also, we have the wing and engine at the eyes. We have the engine start and the electronic engine control computers, or the auto start system for the engine. The fuel tanks and the fuel pumps, the left and right wing, and the center tank, and also the fuel jettison. We have the cabin pressurization and the outflow valves, compressor we use for cabin pressurization, mainly for wing and engine ABIs, for the hydraulic pressurization, and for cabin ventilation and air conditioning. So I'm gonna start showing you all the systems. You can see here the cockpit we have. You can see the flight controls, the yoke of the Boeing 777, also the rudder pedals. We have the steering wheel here, the tiller for the nose wheel steering. We have the landing gear here. You can see we can extend and retract the landing gear, the auto brakes. Here is the parking brakes. You can see the stabilizer trim cutout switch. This is the electric trim cutout switch for the horizontal tail stabilizer. I'm gonna talk to you later. So I'm gonna start with the display, the primary flight display, the navigation display, and then the autopilot flight director system. So you can see also the outside view here of the Boeing 777 300 DRX airplane. So you can see here we have the primary flight display. You can see the airspeed and the ground speed, which is 0 right now. The barometric altitude above sea level 1430 feet for this barometric pressure, 29.92 inches of mercury. So you can see here we have the magnetic or true heading, the magnetic compass, and the heading select. We have the radio altitude. We have the flight director crossbars here. The altitude is 2 feet above the ground level. You can see the flight director, the pitch ladder in degrees. Each tick represents 2.5 degrees, 2.5, 5, 7.5, 10 degrees right here, 12.5, 15. So you can see also in the bank angle, we have similar degrees limit. We have the angle of attack of the aircraft. We have the airspeed select and the altitude select from the autopilot flight director system. The flight mode annunciator with the auto throttle and the vertical and the horizontal navigation. So you can see here the autopilot and flight director system panel. We can select a different value for the autopilot for takeoff, and this will display over here in the primary flight display. We also can select a different altitude for climbing after takeoff. So you can see the altitude here displayed. We can select the 1000. I will select this one. It's more convenient for this flight. You can select also hundreds and thousands of feet. I can see the indicated airspeed Mach, the autopilot engages, the flight level change, some modes of the autopilot disengage switch here. The heading select, I will select a different heading here. I will select the runway heading. So we can press this to select and press the altitude hold, press the heading hold. We'll select maybe the autopilot on, I'm not sure. So you will see displayed here the flight director heading holding the altitude. We have the altitude here 25,300 feet, just like in the autopilot panel. This is for the flight guidance of the aircraft. For the airspeed guidance using the auto throttle system, which is going to arrange automatically the thrust lever's position after during the takeoff or and after takeoff and during the whole flight, mostly the whole part of the flight, unless we select disconnect the auto throttle. You can disconnect it using this switch here. This disengages the auto throttle system, the automatic thrust. So this engages the takeoff go around mode. This is the thrust reverse over here. You will see this thrust reverse being engaged over here. So we have reverse thrust right now. This makes the aircraft slow down in the ground. You see the red with green in the upper display. This is some messages here, some warnings. The outflow pressure from the engines and the total fuel in thousand pounds. So if I go in the outside, you will see here the thrust reverse is open and slowing down the aircraft. We can close the reverse thrust. We don't need that. This reverses the bypass stage of the engine, of the turbofan engine. You can see the front intake of the turbofan engine. How to set up the thrust reversers. Okay. So we have pretty much like we have quite a few time for that, so we have about an hour left. So this is how you advance the thrust levers here. So if you advance them fully here, you will see I told you the N1, which is the low speed low pressure compressor stage of the turbofan turbocharged engine. You can see the thrust lever position here, the front needle. You can see the difference between the position and commanded and the actual thrust. It takes some time to adjust the thrust. You can see the upper limit 104.6%. The exhaust gas temperature per engine, left and right engine, the outflow valve, the duct pressure also increases. You can see duct pressure. This is for the cabin pressurization. The cabin housing is the total fuel housing is the Boeing 777 our airplane. The N2, which is the high pressure, high speed rotor stage of the engine of the turbofan compressor. Turbocharged engine, fuel flow per engine per hour, oil pressure, oil temperature, oil quantity, and the vibration of the engine. So this is the flight management computer also. You can see I can decrease the engine. This is the fuel flow to the engine. You can see here is the flaps position. This is related. This increases the surface area of the wing, so you can extend the flaps and retract them like that. Extend them fully. Also the speed brakes over here. You can see the speed brake mess. So you will see the flight, the secondary flight control surfaces here being extended in the outside view. You will see the flaps coming down. You can hear the hydraulic fluid. So you will see also the speed brakes, as I said here. This slows down the aircraft inside and in ground after touchdown. The speed brake. Also the pitch stream position here, nose down and nose up, the engine's position. So I'm gonna show you a few more things about this system. So I'll show you some of the autopilot. I'll show you the speed select, the heading select, the altitude. We also have the vertical rate of climb and descent. So it's another mode you can select here. Climb, descent, right now minus or plus 2000. You can see the VS. We also have the flight path angle here switch. We have the heading track here. You can select heading track to this small button. You can see the heading again. FPA, VS, FPA. You can change this using this small switch over here by pressing this and using this slider up and down to move the switch. So you have engaged now the vertical rate of climb and descent. You will see the VS now as flight path angle for the aircraft to follow, for flight following. So you can select the LNAV, the VNAV, the flight level change. So when we select the speed guidance, you can connect the autopilot now. This switch over here. You can see the glide continues, the auto throttle hold switch for the thrust and the flight level change. So the autopilot now is engaged. You will see the APs here displayed in the primary flight display. The autopilot is engaged for flying the aircraft. So you can disengage it by pressing this switch over here. You can also move the flight control surface. So you see the flight director now on the warning. The autopilot is disconnected for this aircraft. So you cancel the warning, you engage the autopilot again. So you see the AP again engaged with the crossbars here for the flight guidance of the aircraft. So you can use also this switch over here. The AP disengage here to disengage the autopilot. This is the autopilot disengage standard switch. So you can see the AP engaged here and the autopilot disengaged. So we press this, you will see and hear the warning again. The autopilot is disengaged. Autopilot disconnect. So we the position here of the switch and cancel the warning. So now we have the flight director to fly the aircraft manually. So I forgot to show you the navigation display. I told you displays the terrain around the aircraft. You can see also the weather. We have the radar over here in the navigation and communication panel. You can turn it on like this using these switches over here and select the modes you will display. Also the strength of the beam. You can select also this the TIC system, the traffic collision and alert. You can test it also. You can press the switch. This is a transponder that transmits our position. You can see the test of the system, traffic collision and alert system. So we have a few more minutes left to go. You can see inside the cockpit. I will show you as many things as I can. The overhead panel, navigation and communication panel, the fire extinguishers for the left and the right engine, the fuel flow to the engine, the fuel control switch, the stabilizer corridor, the stabilizer trim, the radio navigation communication radios. So this is the transponder that transmits the ADS-B or the ADS-C that transmits our position and our altitude and our direction to other aircraft over here, and also receives from other aircraft. So you can see another aircraft flying over here. It's quite close to us. You can see it here displayed in the radar display, and it's 2,800 feet above us and is moving in this direction, displayed with this white diamond. we have another aircraft, so I will select the further range. You can see also other data. You can see the terrain level displayed with green, red and yellow. You can see that the red is 6,100 feet over here, the terrain. It's the mountains of the Switzerland. The Alps with green is 0 feet, with the yellow is intermediate. As you can see also the sea, the rivers, the lakes with blue. You can see some airports. You can see Switzerland airports, France airports, and Germany airports over here. This area is Germany, this area is Switzerland, and this area is mostly France Valley. So we're gonna be overflying Germany. So you can see also some other systems. Here we have the FS panel that controls the displays over here, so you can select airports, waypoints, radio navigation. So we have the position, the GPS position, the wind direction, the magnetic track here, the flight plan. I'm gonna show you flight plan. We're gonna be create horizontal and vertical guidance flight plans. So we have pretty much like 40 minutes left for this flight, 50 maybe minutes. So no, it's actually like 40 minutes more. So I'll have to be like more fast right now. Show you the rest of the systems, the navigation display, I'll show you the ACAS, the upper and the lower ACAS, the autopilot panel, the modes we can use with the autopilot. So I'm gonna show you now the flight controls. This aircraft and every airplane, like this airliner that has turbofan engines, we have two turbofan engines, one installed per left wing and one installed for the right wing. We installed two turbofan engines for redundancy, and also for having symmetric thrust during flight between the left and the right wing, not asymmetric thrust, so we need two engines. So these engines, when we move the thrust levers forward, they increase the fuel flow to the engine. We do that and have a more spin of the engine's rotations and increases the engine rotation spin. This makes the compression of the air, the rate the compressor is receiving to the engine increases and makes the burning of fuel into the engine faster. This increases the expansion of gases in the exhaust in the back side of the engine. So we have a difference of pressure between the forward and the back of the engine. That makes the aircraft move forward by means of action and reaction using the Bernoulli's theory and the Newton's physics, the first, second, and third law of motion, kinetic motion, the mechanics, the Newton's physics and Newton's mechanics. We can make some conclusions about this. So we have, as we increase the fuel flow into the engines, that makes the aircraft engines move faster, burn fuel faster, and expand gases faster. Because we have turbofan engines, which is kind of turbojets. So this makes the aircraft acquire airspeed and kinetic energy. The kinetic energy of the aircraft is 1 second its mass times its velocity to the power of 2 using the Newton's physics again. So you can see the thrust levers here. We move this forward, we need to move them forward to make the aircraft move in the ground and start moving. After we move the aircraft in the ground, actually in the runway, we need to take off the aircraft. So in order to take off the aircraft, we need the forward thrust from the engine. The thrust overcomes the drag from the air friction. When the aircraft has a sufficient airspeed, for this aircraft with this fuel quantity and this load, right now it's 253,000 kilograms, we need an airspeed of above 154 knots with 15 degrees flat for takeoff. This is the takeoff speed setting every time I use this aircraft with 4 degrees speed spring, the horizontal tail stabilizer. This is the horizontal tail, the stabilizer. This is the forward wings. This is the engines that move the aircraft forward. So the forward wings create the lift when we have enough thrust from the engines and enough airspeed. So for this takeoff we need 154 knots or about 270 kilometers per hour. We can take off with a little bit less airspeed, like 250 kilometers, but it's gonna be like completely marginal to the stall speed. So we need to be above the stall speed because the stall speed is not enough to create enough lift to move the aircraft up into the sky, and the aircraft is gonna stall and fall into the ground. So we need to be careful with that in takeoff and during flight. Avoid the stall speed. We need to have enough airspeed to create enough lift. The lift force using the Newton's physics, the first, second, and third law, and some aerodynamics and aircraft engineering, and the Bernoulli principle, makes the aircraft flyable because the top surface of the aircraft wing is more curved. It has a curvature. While the bottom surface of the forward wing it's flat, so the air mass, the airflow is traveling faster to the top of the wing and it's traveling slower to the bottom of the wings of the aircraft. So the bottom of the wings of the aircraft have higher pressure when the aircraft reaches its effective airspeed for takeoff, while the top surface of the wings, which are curved, have lower pressure. So we have a difference of pressure between the top and the bottom of the wing, and this makes the bottom of the wings press the aircraft wings up into the air, while the top of the wings makes the aircraft being stuck up into the air in a vacuum. So this creates the lift force that makes the whole weight of the aircraft 253 tons in this case to move up in the sky while we take off with 270 kilometers an hour airspeed and hold it in the air while we fly. So we need a constantly thrust from the engine to counteract the drag from the wing, from the air friction, and we need the lift to counteract the mass of the aircraft times the acceleration of the gravity that pulls down the aircraft into the ground. So this is the theory of flight for the aircraft using Newton's first, second, third law of physics and the kinematics, and it's also aerodynamics and aircraft engineering and aerospace engineering. So this is used also for the piloting of the aircraft, principles used for pilots. So this is simple. So about 35% of the mean aerodynamic chord position of the forward wing is the position of the maximum aerodynamic lift pressure in the top surface of the wing, not the bottom. So in the top surface of the wing we have the aerodynamic pressure position of the Mach, 35% of the mean aerodynamic chord, the forward wing. That makes the maximum lift component, and it's also used to calculate the stall speed of the aircraft when we pick up the aircraft wing too much, or we have a slower speed. So also this is the position where the center of gravity usually is positioned, at, forward, or up this position. So it makes the aircraft forward center of gravity or up center of gravity. To the position of the aerodynamic cord, aerodynamic pressure in the wing, in the forward wing. So sometimes it's exactly positioned in the same section. So you can see here we have the mean aerodynamic cord position, 35% is about here. So this is the maximum lift position. You can see the bottom surface of the wing is flat. So this makes a higher pressure under the wing. And the top of the wing is curved. It has a curvature, an arc, so it makes the air travel faster, the top of the wing. And this is due to the Bernoulli equations in theory. So you can see the curvature of the wings, the forward This makes the center of gravity axis is located about here usually, and you can move it forward or up depending on where you position the load of the aircraft, like the fuel and the passengers, and also where you install the engines and other stuff like the tail also component. Also you can have some more things you need to know about flying the aircraft when it's flyable. We need the directional stability of the aircraft in flight. So we use the flight control surfaces like the horizontal tail wing with the elevator, which is a separate wing that can move up and down, and the vertical tail stabilizer with the rudder, that is a separate surface in the wing, in the vertical tail wing. So you can see the horizontal and the vertical stabilizer here. And this axis of the horizontal and the vertical stabilizer that creates once the aircraft has an effective airspeed for flying, it creates enough lift. It also has effective flight control. When we move the elevator up and down using the yoke or the side seat, it also deflects the airflow mass in the tail of the aircraft. So it makes the aircraft pitch up, pitch down, and also the vertical stabilizer makes it turn to the left or turn to the right. And also the ailerons and the spoilers in the left and right wing also make it to bound roll to the left and right by deflecting the airflow mass and we fly. So we need to have effective flight control and effective lift and effective airspeed for flying this aircraft using the thrust from the engine, the forward thrust. So the thrust from the engine makes it only move forward, not move upward. It's the wings that make it move upward. So the lift from the wings. So you can see all these things here, the flight control surfaces, the ailerons, the spoilers, what I mean. So you can see here is the center of gravity, the dynamic chord position, and the maximum lift in the forward wing. So the horizontal tail and the vertical tail create a moment arm. You can use again Newton's physics, first, second, and third law of motion of physics. So the moment arm is the force times the mass of the aircraft component or the mass of the airflow it deflects. In this case, the horizontal and vertical tail in the ailerons in the left and right wing. And this is the mass of the air per second times the pressure times the velocity to the power of 2, and also this is mostly for a different reason. It's actually times the mass airflow times the distance from the center of gravity. So this is the moment arm, and this is also times the gravity of the Earth. If you use it differently using the aircraft component. So you can see the moment arm here, the lever arm, using the Newton's physics. So it's the force times from this here, from the center of gravity all the way down to the tail, and transverses forward from the nose of the aircraft. And it makes the aircraft pitch up, pitch down, and also turn left and right. So this summarizes dynamics in an aircraft engineering principles. So when we bunker the aircraft left and right, we also have G-load, differential load lift and G-loads from the wings, from the left and right wing. This makes the wings that have less lift to move into the side we turn. So if we turn to the left, we have more lift to the right wing and less lift into the we will turn the left wing. So if we turn to the right, we have more lift to the left wing and less lift into the right wing. So you have to know something about flying the aircraft. So I come again into the cockpit. So you can see here we have the control yoke, the control column, and the control wing. Makes picks up and picks down the elevator. So you can see I'm using this this side stick here for flying this aircraft, which is an Airbus side stick, but you can use it for the Boeing, so you can pitch up, pitch down the elevator, also bang roll the ailerons, and also the rudder pedals for turning the aircraft left and right, and using the nose wheel steering in the ground. You can use the stabilizer trim position here, so I hope you like it. You can see the position of the side stick is proportional here to the position of the control wheel and the control column as I move this over here. So you can see also the thrust levers position here. Need the parking brake. So you can see also the outside view here. That I'm using the flight controls like that. Pitch up and pitch down. The elevator, the rudder, also the aileron for the spoilers. So you can see again I'm using pitch up, pitch down, bang roll left and right, and the rudder pedals and the nose wheel steering in the ground. So this is how you use the flight controls inputs. You can see it's proportional to the side stick deflection, the movement of the tail of the aircraft, of the elevator. See it here. And also bang roll left and bang roll right. The bang roll position. So this is so much for the flight controls. Right now I'm gonna show you a little bit more inside. You can see again here we have a proportional movement. So I'm gonna show you also some more things about the aircraft now. You can see the horizontal, this is a secondary flight control, the horizontal tail position. I told you you can use this switch here to position up and down the horizontal tail trim. So I'm gonna show you a couple more things. I'll show you the thrust levers. You can see the trim position here, the horizontal tail. Right now it's 4 degrees up for takeoff. You can see nose down and nose up. You can see the pitch string alternator normal, and here we have the cutout safeties for the pitch string, for the alternator and the normal pitch string. So you can turn on and cut out the electric trim for the autopilot and the auto throttle, but it's better not do it. So we have the speed brakes here, secondary flight control, and the flap position. So I'm gonna show you in a couple of seconds. I'm gonna show you some things about the overhead panel. You can see here we have the displays, so you can see this display here. We have the on display. In the synoptics we have the flight controls movement. You can see full flight controls, deflection here. So you can see here we have this flight control movement for this aircraft, just like the original when I move the yoke of the Boeing airplane. So I'm gonna show you a couple more things about here, the systems. So we have like 30 minutes left for this flight. So we have some system, we have some modes. I'll show you the engines. We have the status. We need to turn on the APU. I will come in the overhead upper panel here. You can see this view here. We have the upper panel of this airplane. So I'm gonna be more fast now, maybe not having so much time. It's better complete this setup right now. So you can see here we have the ADIRU, the Air Data Inertia Reference Unit. We'll talk to you later about that. We have the auto throttle, the flight controls, primary flight controls, the thrust symmetry compensator, the ADIRU, the Air Data Inertia Reference Unit. I will tell you about later. So we use the start the APU. You can see the electrical. We have the left and the right engine. electrical, I will show you in the displays. We have the left engine drive and electromagnetic alternator, 120,000 kilovolts or 120,000 watts, alternated 400 Hz frequency, 120 volts to 200 volts. Its electromagnetic alternator is bipolar north and south pole with electromagnetic induction to create this alternate current. 400 Hz frequency, 120,000 kilovolts, left engine and right engine. This is driven by the turbofan engine drive gearbox, drive an assembly with other systems. Also the backup generators, 25,000 kilovolts each, left and right engine, and also we have the APU, the auxiliary power unit, another 100,000 kilovolts, 400 Hz frequency, 120 to 200 volts on each. And we use this for starting the engine. This is when the engines are normal and working. This is the battery and the APU battery. We need to start the APU in the aircraft in the ground. So you can see the systems here. You can see I can move the throttle lever, so here is another view. Also the speed brakes again. The flap position here. I will move the flaps out to 15 degrees maybe for takeoff. Over here you can see I can move 20, 25 and 30, and this displays over here above the fuel. You can see also the landing gear here, down and up, throttle levers, position, some warnings. The landing gear, you can see the retract and extend limits, the auto brake, the alternate gear here, some other switches I will tell you later. We have also the autopilot again. This switching here, you can see a better view of the autopilot. So we have in the overhead panel, we start the APU. We have also the hydraulic here, the left and the right engine driving. Hydraulic pumps, you can see I can turn off the controllers. We're gonna have some messages here, some loss of some systems. So you will see hydraulic pressure going off from the flight controls. We lose the stabilizer left, C and right. The autopilot disconnects. So if I come here, you can see thrust asymmetry compensators message. So this is the hydraulics. We lose all the hydraulics. You can see the pressure down is 50 psi. Also in the flight controls, we have no flight controls now. It's cross. And we have the hydraulics ACR here, message, fold message. So there is no actual flight controls here for this wheel, for this flight control. Also no rudder pedal or the first of it is not a good condition. So I need to come here again to reconnect this. You will see if I come in the overhead panel. If I restart the hydraulic pumps here to the on position, the engine driving and the electrical, this is gonna cancel this message here, this fault. So you're gonna see the fault messages going off. So we can also disconnect the engine driving electrical now. Because we have the APU, we'll see the message here, electric generator off right, the backup system also. So this is warnings in case you lose our system. We have some other systems like the window heat, passenger oxygen, ground proximity, cargo fire. Here you can see electronic engine control for the engines, the FAREX that I told you, control the engines, and also auto start. On and off. You can start the engines like that. We have the fuel jettison. You can dump fuel like that in the air. If we arm this, we'll see later. The fuel tanks, left and right fuel tanks. On the wing, also the pumps, the exit valves, the pressure you can turn on and off. So I will come very quickly into the system. So we have the engine and the wings RDI system here, some lighting system, the windshield wiper here, the cabin pressurization outflow valves, automatic and manual, open and close position here when we climb or descend the aircraft to pressurize manually in the manual. So in the automatic we don't need to do anything. And we also have the left and the right engine outflow valves. I will show you, and the APU outflow air. This is the compressed air. So you can turn off firstly here in the system, because now we have the hydraulics full of power. Over here we have only the air disconnected, so we do not have pressurization on the air. We have the electrical left and right engine, the volts of the battery, the APU is on. So we have also the fuel, the left and right engine, the total fuel quantity, the engine symbol. You can see the green line means there is a fuel flow. The engine fuel on the high pressure fuel valves are open. The APU also. You can see the quantity in the left and the quantity in the right wing, and the center is no fuel in the center, and about 51,000 pounds in each wing. So we have the air system here. We close the duct pressure. So this is over to the upper panel. We reconnect this system. We need the APU compressed air for starting the engine, and we need the engine left and right, and the engine right compressed air. This is the compressed air, the fuel, the engine start, the hydraulics, and the electrical, the flight control computers, and the GPS and inertial positioning. So this is all the systems of the aircraft. I'll show you here. So you can see now we have the compressed air for cabin pressurization, for wing and engine, and the ice, and also for starting the engine using the APU. So also for air conditioning, you can see the temperature into the cockpit. We have the doors are closed and the cabin is pressurized. We have the landing gear here. You can see the temperature and the pressure inside the tires. So we go into synoptics again. So in the virtual cockpit, we turn off the left and right engine driving the fuel flow to the engine. So we have about 36 minutes left for this flight. I'm gonna try to be as brief as possible. So you can see the engines here are off right now. The left and the right engine are slowing down. So we're gonna turn them on again. You can see no spinning. We're gonna turn on this switch over here. The auto start for the left engine. So this is gonna admit compressed air from the APU into the left engine system. You will see the start sequence. The N1 increases, the exhaust gas temperature increases, the N2 also the fuel flow is 0, so above 35%. You will see here the compressor, the engine start compressor is spinning the left wing engine faster and faster, so we can admit the fuel now. You can start the fuel flow, so you can start the left wing engine like that. So you will see the N2 and the fuel flow is 0, it will become higher, above 0.1, 1000 kilograms right now. So this makes the engine spin faster now. We have normal operation of the engine. So here we go. We have this wing engine start. So we go in the right wing. So this is off right now. We need to start the right wing engine now. We have a couple more things to do, and then we're gonna fly the aircraft. So we start the auto start here, the automatic settings. So we have again the same factors over here, same data for the right wing engine now. The N2 above 20%, the fuel flow is 0, so you can see the spinning here in the right wing engine now. You can see the wings of the Boeing. So You see the engine spinning faster, so we can start the right wing and the fuel flow valves on. So you will see the fuel flow increase from 0 all the way up for the right wing engine. So here we have the right wing engine start also. Start spinning. And here we go. We have both engines running normally. So we only need to do one last step here. One last step over here is this. We need initialize the flight management computer, so we create a flight plan. We need the positioning of the aircraft, the IRS position, inertial position, the GPS position over here, the reference airport, and we're gonna use this route from this runway, from this airport. Using this runway, Lszh, runway 14, destination again, Lszh. So we have the initial, the gross weight, 0 fuel weight, gross weight in thousands of pounds, the reserve fuel, the total fuel, the flight altitude, and the cost index, 100%. So we use this departure and arrival for this airport, Lszh 14, trans this, departure and arrival, Lszh 14 again, trans this, Negri 1 Alpha, trans Yamakee. So we have the leg, we have the departure and the arrival, so we cancel and we activate. The thrust flap limit here, the center of gravity for takeoff with 4 degrees, this is the takeoff reference, and the V speeds, 133, 140 and 154 with gross weight 580,000 pounds or 235,000 kilograms. So we need 154 knots. We're ready for takeoff. I'm gonna advance now. You can see where we are now. We have quite more than 20 minutes left for this flight. So we need to go now. Advance the thrust levers and disarm the parking brakes. So you can see I'm using this wheel here, this pillar, alongside with the rudder pedal to steer the aircraft in the ground. So you can see the runway is open for us for takeoff. So we taxi into the runway. So here we are, we have about 30 minutes left to go. We align with the runway. One last side view here, where we are and where we go, and a nice takeoff view here. So you can see the autopilot is set. We only set the VL now. We have the airspeed here, the heading of the runway, the altitude we desire to fly. The flight director is on. You can see the Lszh localizer here, the crossbars, the altitude right now of the ground. You can see the ground level, this symbol, the airspeed is 0 right now. So you can see the flight plan here. I will show you in this position. You can see this line is the flight path we have to follow. So we advance the thrust levers. You can see the flaps is set correctly. So advance the thrust. You can see the thrust increases all the way up to the takeoff limit. So disarm the parking brake again and go. So we have like 100 knots right now, airspeed. We have V1, V2, Here we go. We have a positive rate of climb, so we drag the landing gear here. So you can see it just picks up with the control wheel, control column. So you can see the rate of climb. We are 1,600, 1,800 feet above the ground level, 2,000 feet above the ground level, 3,700 barometric above the sea level. Rate of climb 5,000 feet per minute. So we need to use maximum rate of climb right now. We're traveling with Mach 0.419 or 500 kilometers an hour. So you can see the climb out here as we're climbing. We also have the terrain data. Here you can see I'm using this steering wheel and the control column. So we have 18 minutes left for this flight. Climbing up with maximum rate of climb 9,000 feet above the ground level. 10,000 above the sea level actually. So above the ground level we are about 8,000 feet. So you can see the Boeing 777. Hope you like it. You can see we are overflying most of Switzerland right now. We have the airport here in the back and a beautiful view over here. You can see this is flying with 500 kilometers an hour or 250 meters per second. Quite a lot of airspeed, you know. And we climb very fast. So this is the Boeing 777-300 VRX airplane. This airliner, beautiful Boeing 777-300. Hope you like its engines, magnificent view. You can see how fast we're going right now. You can see we're gonna be overflying the lake. So coming back, maybe having another speed right now. Yeah, a little bit of overspeed. So this is us flying this airplane. So we have 33. So we have about 13 minutes left for this flight. 13 minutes like that. So climbing 18. We have a little bit more time than the other time, I believe. A little bit more time. So maybe gonna see a little bit more view here, better view. Just fixing this the direct to I was telling you. So direct to the next waypoint, the leg. You can see the leader here. So we're gonna fly here and the arrival of the limits for landing, the landing reference here in case we go for landing. So now we're flying direct to this waypoint here. You can see the data we have in the display as we climb into this 1,000 feet, flying manually. So you can see the data we have, the flight control, flight director here to the 1,000 feet. This was the flight director rate of flight. The climb was 2,500 feet. The airspeed is Mach 0.515 for about 650 kilometers an hour, or about 250 meters a second. You can see the upper limit is the flaps we have extended, and the green bunch here is the stall speed we need to avoid because we're gonna stall the aircraft. If we go below this yellow line, we need to keep the airspeed above that. So we are 33,000 feet, start having flying with 200 meters a second, 250 meters a second. Later we're gonna be flying with 300 meters a second. So this is our spacecraft for tonight, the Boeing 777-300 RX, 24,270 feet above the Alps. So in front of us we have the lake, this beautiful lake, the St. Gallen lake, and we have also Germany in front of us. We have the Bayern Munich region. So we have the galaxies here, the night sky view, this beautiful view of the Boeing 777 overflying Zurich here in Switzerland with 600 kilometers an hour, about 6,000 meters above the ground level. So here we reach our flight altitude. We are 35,000 feet. Need to level up. We have like we have 13 minutes left for this flight. So we need to start going back into the airport. Here we are level off, 35,000 feet here. We need also to bankroll into the airport. Let's start an early return into the airport using manual inputs. Also a little bit less thrust from the engine. So retract maybe the flaps. We don't need so many flaps here, and use a lot more airspeed to go back into the airport. So we're gonna be flying with 300 meters per second, or about Mach 0.8. So we need to make an early return. You can see the Alps here. We are 6,000 meters above the sea level, about 5,500 meters above the ground level. So this is making turn here. We're flying Switzerland, the lake, the St. Gallen. We have Germany on this side, the Bayern and Bavaria, the Bayern Munich, the München, Germany. So we need to level up a little bit. Turning back into the airport now. Flying with about 300 meters a second. This beautiful airplane. So you can see the frozen vapors here in the back as we bankroll. So we need to go back inside. Turn faster. Maybe use the autopilot connect now command with a level off at this altitude. So we're gonna level off. We have the autopilot command on. We need to go direct into the airport. Maybe the headings select. We have like direct into here into this runway, execute, and use again the Lszh, the autopilot connect with the Lszh. So this is gonna fly us faster into the airport, and we have like have like 9 minutes left for this flight, I believe. So this is quite 8 minutes left for this flight actually. 8 minutes, so it's a lot of time to look around. Here we are flying almost level with the autopilot command. You can see the AT1. We need to start descent. We are just 34 nautical miles, so select a lower altitude now. Target altitude over here like 6,000 feet, and also VS vertical rate of descent, and also a little bit less airspeed. So we need to extend the speed brakes now to slow us down, and also less airspeed. So you see here we start the descent of the aircraft. We cross 33,000. So this is our spacecraft looking at the Boeing 777-300 going back, having 8 minutes. A beautiful star sign here. Flying with 900 kilometers an hour, about 300 meters per second. We're flying this beautiful Zurich region here, Switzerland. So we're very close into the airport right now. Much closer. You can see the rate of descent. We need to slow down. Disconnect the autopilot actually. Fly the aircraft a little bit manually. Use also the Lszh localizer mode here. We need to slow down the aircraft a little bit. To cross 13,000 feet. Extend the landing gear now. We need the landing gear here, down. So this is gonna slow us down a little bit. So we have like 5 more minutes left for this flight, which is good. We can slow down the aircraft after this descent. You can see where we are as we go into the runway. We're overflying the river right now. You can see the landing gear is down. Making a nice turn here. 1,000 feet. Going down. I'll cancel this autopilot with the maintenance. So this is the river over here. We have the clouds. We can use some flaps here. This is gonna help us land. You can see the status of the aircraft here. We're gonna use an Lszh localizer landing. So we have some overspeed warning. Making some hard braking maneuvers, meaning to slow down the aircraft as we descend into the runway. Also lose some altitude. So here we are in front of the runway, almost reached the runway. Flying manually, as you can see. So here we are. So this is our position near the ground, very close to the airport. We have like 3 more minutes left to go. We're flying the river again. We have to align here ourselves, so fly a little bit faster. We have like 3 more minutes left for this flight, which is not too much of time. So we need to apply some more thrust as we descend. So we have the Lszh localizer here. You can see the runway, you can see the terrain. We have the Lszh localizer. We are 2,480 feet above the ground level, flying with 193 knots, and we are 3,000 feet above the sea level. You can see the difference between 2,000 feet above the ground, 3,400 above the sea. You can see the Lszh localizer, the glide slope. We are aligned with its runway right now. So we need to make one small turn as we approach Flught. So this was the Lszh localizer inputs with the horizontal and vertical localizer. The airspeed, we need to pay always attention of the aircraft, and the rate of descent. We are in the glide slope right now for descent. Descend with about 190 knots, 200 knots right now, 360 kilometers an hour. Descent. So we are aligned with the Lszh localizer. One small alignment with the rudder pedals here, and also bank roll with the yoke. Here we are, so close into the ground and the runway. We go with 170 knots, about 300 kilometers an hour landing. So here we are, 100, 50, flare, 30, 20, 10. Here we go. Just landed. Reverse thrust and park and brake. So we use the reverse thrust, full reverse, and align with the rudder pedals. So here we are, just landed into the runway 14 to the National Airport. You can see here the nose wheel